Hello, welcome to session number 22 in the series Microwave and Millimeter Wave Circuit Design. I am Anurag Nigam, and in this series I'm going to present to you how do you do a modulated source and put that modulated source signal into the PA, and the output of the PA you are going to plot the spectrum and compute the ACPR. So let's go ahead and do that. So what you do is you just create a new schematic, right? Now I'll tell you one thing. There are two ways of doing this. One way is you do this in a circuit simulator, and then the source works in the circuit simulator. Other is you can take your circuit to a behavioral simulator like a Talmy, right? In Talmy, you have what you call it crunches numbers like zeros and ones. It doesn't have a timed information. So basically you have your circuit enclosed in a lower hierarchy, right? And where you do the envelope simulation or the time simulation. So you take the result of the time simulation back into the Ptolemy, and then you can analyze the results, right? So there are two ways of doing this, right? Either you bring the bench or the source into the circuit simulator, or you take the circuit to the behavioral simulator like Ptolemy, right? So we are going to do one way, and then we are going to attempt the other way. So let's say I am going to do a study on ACPR study. Okay, so we are going to look at the non-linearity, right? So we are going to look at ACPR. Okay, so what you need to do is you just put in what is called a modulator, right? So let's say I'm going to start with a very simple DQPSK, differential QPSK, pi by 4, right? So you go to sources modulated, you will find modulated sources here, but I will show you how to set this up using what you call a modulator, right? So let's look for a modulator. System modulation and demodulation, right? Here you look for this is going to be QPSK, DQPSK, right? So this is DQPSK. Okay, so I am first going to modulate the signal, right? So I'm going to write a set of equations. Okay, so to write a set of equation, I'm going to use this var. Okay, so first of all I need to know the bit rate. Okay, and let's say that this bit rate is 76 megabits per second. Okay, so this is your bit rate. Then we are going to do a QPSK. DQPSK is a form of QPSK. So basically you are taking two bits and forming a symbol. So the symbol rate is going to be half the bit rate. So symbol rate is going to be half of the bit rate. Bit rate by 2, right? Okay, so the next thing I'm going to discuss is how many symbols am I going to analyze. So num symbols, num sim, right? So let's say I'm going to analyze 300 symbols, for example, just arbitrary number. Then I also want to see how many samples per symbol. Samples per symbol. Okay, let's say I'm going to do 10 samples per symbol. Okay, that's a typical number, right? Next thing, I want to find out what is the time step or t step. Okay, so that will be the sample time, right? So that you can find as 1 divided by symbol rate. So that will give you a symbol time period. Okay, so it's 1 divided by symbol rate, that is going to give you symbol time period, and then there are 10 samples in that. So simple time period divided by the number of samples per symbol, right? So samples per symbol, sample per symbol. Okay, and t stop is going to be total number of samples num samples, total number of samples, num or total number of symbols, sorry, total number of symbols multiplied by the uh, okay, multiplied by the symbol rate, uh, number of samples and samples per symbol, right? Number of samples uh, multiplied by samples per symbol, samples per symbol. So this will be the total number of samples, right? Samples per symbol. And then you multiply it with t time step, t step. So that will give you the stop time, right? Add stop time. And then you know that we are going to use some kind of a DSP filter. And DSP filter is nothing but these are what you call these are z minus 1, basically delay by a sample, right? So basically a filter has a certain length of number of symbols or samples, right? And you specify the filter length as that. So this is going to be some form of a FIR filter, right? So I am going to say that the filter delay basically is at least half the filter length. Okay, so let's say the filter length is 16, so then the filter delay is, let's say, 8, right? So 8 symbols. Okay, so I'm going to put here FLT delay. Okay, and that I am putting as 8. Okay, so I guess I have everything in place here. So now I also need the RF frequency, right? So I want to put here RF and RF frequency, and that is 6.5 gigahertz. Center band frequency, sorry, 6.5 gigahertz, right? And RF power, that for now I am going to start with 0 dBm. Okay, so I guess we are done with the variables. So now I am going to put here a source of a carrier source, which will be a P1 tone, right? So this will decide the carrier power and the carrier frequency, and I'm going to modulate that with a random number of bits, right? So here I am going to say that this frequency is RF FREQ, and sorry, RF power, RF PWR, and then the frequency is RF FREQ. Right, so we are set up with the carrier power and the carrier frequency. Now this should be also working at that carrier frequency, right? So it should be RF FREQ, correct? And this is the symbol rate, right? So this will be symbol rate, right? And this I will put a delay of 0 nanoseconds. That's okay. Then I want to put a random number generator here, right? So for that random number generator I need a time domain source. So let's look at VT-LFSR, left shift register with feedback, right? So this is the one, right? Okay, so what it needs is a certain tabs. I can put it in binary, or I can put a number here, for example number here, and then it needs a seed, which is a start value. Okay, I can put any number here, right? Start value. Then I need here rate, so this rate will be bit rate, bit rate. And then I want this to be a bipolar signal, so -1 and 1. So I'm all set here to put in random number of bits here, and these bits are going to be bunched up into 2 bits as a symbol per symbol, and then they are going to do a differential QPSK out here, right? So then what I can do here is I can filter it. So I'll show you why I put a filter. So here I will put here a DSP filter. So I will go to filter band pass. Okay, and I will look for a raised cosine filter. So that's a raised cosine filter, correct? And here I am going to have alpha. Alpha is basically excess bandwidth. So if there is a cutoff window, right, as we have seen in the filter, we have certain excess bandwidth. So that is 35% here, 0.35. And then the center frequency is RF FREQ. RF FREQ, correct? And this would be symbol rate. Symbol rate. And this is going to be filter delay. So this is half of the filter size. So filter delay will set the filter size. Filter delay and sync E. Yes, and then this is going to be a 50 ohm. So this filter is done. Next is I am going to put my old PA. So I will take this the symbol for this. I will take the model for this PA which I have been using earlier. So I'll take the entire thing like this. Control C and Control V. So that entire thing comes in here. So I'm going to take the modulated signal and which is filtered and put it into a PA, right? So now let's name these nodes because I want to see the constellation on these nodes, right? And then after that I want to compute ACPR, right? So let's do that. So for that, let me name this as VIdeal, correct? And this one is V filtered, VFLT, right? And this one is V out. So we have covered everything here. The gain is 20, and then so the gain here is roughly 20, right? So yeah, so and it is going to compress at 30 dBm, right? So that's what we figured out, right? So we have to put in 10 to get the 1 dB compression point, right? So now I am going to do an envelope simulation, right? So where is this envelope simulation used? Whenever you have a signal which is modulated, right, then there are two time bases. One is for the carrier, the other is for the baseband. Now how many cycles of baseband you should cover? I am using 300 cycles or 300 symbols, right? So how much should be the stop time? The stop time is decided by at least a few cycles of the baseband, right? And what should be the sampling rate? The sampling rate should be as per the carrier frequency. Now if you do this in time domain, what's the problem? Problem is you have a time period which is from baseband, but your sampling per cycle or the sample rate is from the carrier frequency. The carrier frequency may be in gigahertz. So if you take 10 samples of that, let's say 2.5 gigahertz, you take 10 samples, or 6.5 gigahertz, you take 10 samples per cycle, then how many samples would you be having, right? So now you see how many cycles will fit in, let's say, a baseband which is like few kilohertz. So for a microseconds you have to do simulations, and with a sample of nanoseconds. So in time domain, really this is going to take a long time. So then there is a solution for this. Okay, the solution is you do what is called time stepped harmonic balance. So the time stepping is done as per the baseband, and then the harmonic balance is going to use the fundamental frequency, which is the carrier frequency, and its harmonics to solve it in harmonic balance. So circuit is solved in frequency domain at different time steps of the baseband signal, right? And then the result is combined into the output. So this is the principle behind envelope simulation. So let's put here envelope simulation. Okay, so in this case I would have to have a frequency of oscillation. So in this case, the first of all the stop time, right? The stop time will be T stop, which we have already written an equation, and the step time is T step. Okay, fine. And then the fundamental frequency here is the RF FREQ, the carrier frequency. right? And apply. Okay, and what else do we do? That's it. Say okay. So we are all set with this envelope simulation, right? Okay, so now I have to just hit simulate. I don't have to do anything else unless the equations are wrong. Okay, so the simulation is done. So let's look at VIdeal. So let's look at the constellation. VIdeal, fundamental of that. So as I told you, okay, so if you remember, I told you that there are symbols. So let me just first change the grid. Options, preferences, grid, and 0625. 0625 and one grid, and say apply. Okay. So I'm going to show you so there are two different groups in DQPSK which are pi by 2 apart, right? So I'm going to point out those groups, right? So one group is over here. So let's make this one, sorry. So let's make, come on. Let's make this one as blue colored. Okay, so one group, let's say is, I'm going to pick up here. Control C, Control V, and this controls V, and here Control V, and here. So one group is this. Okay. Then the other group is the 45 and 135 group, right? So this is what I explained in your previous session, right? Control C, Control V. Let's make this as green colored. Correct. So this is one group, which is 135 45 group. Okay. Control C, Control V. Control C, Control V. Control C, Control V. Okay, so you understood that there is a phase difference of 90 degrees in each group, but then the two groups are 45 degrees apart. So this is your ideal DQPSK, right? Okay, so this is your ideal DQPSK, and this is with a power of 0 dBm, right? So now the next thing is I want to draw what happened to the filtered case. So filtered, add fundamental. So you see, now the transitions are not sharp, right? So I will take the entire thing and I can figure out the points. They're kind of, I'll have to sort them out, right? So yeah, so these are the points, right? So one is over here. Which one should I consider? Yeah, so let me very quickly do it. 2, 3, and 4, correct? And then you have got 5, and then 6, 7, and 8. Okay, so you are looking at again the same 8 states, right? Okay, now I'm going to plot the output. Output is going to be the same, but it is going to be amplified. Okay, so it is amplified, is the same output. Okay, now you might question why there was a rotation, because you see you inserted a delay, right? Because you inserted a delay, you got a rotation, right? Okay, so let's just do that quickly. So this is one group, then the other group is over here. sorry. Oh, come on. Okay, so this is the input of the PA, this is the output of the PA, and we are really backed off, so we don't see the effects of nonlinearity on this, right? So you understand, these are at these, so one of them represents VIdeal. Sorry, let me just put here. Okay, so this VIdeal is over here, and this one is the filtered one, and this one, the right one, is the output, right? And you see the scale over here is different, right? 0.5 minus 0.5, so this is plus minus, right? So this is centered on 0. Okay, fine. So this is your constellation of DQPSK when it goes through a PA, the ideal, the filtered, and then the output of the PA. Let's look at the spectrum. Okay, so the spectrum, I'm going to first plot VIdeal. Okay, and I have to window it using a certain window. So this is your VIdeal, and you see that there are lots of spectral components because they are sharp corners, right? So there will be lots of these components which are going to be significant, but once you filter it, then these components are going to go down, right? So if you put your filter here, right, and you say okay, so you now see that all those components are lower now, right? So this is the effect of filtering, right? So you have limited the bandwidth now, right? So all these sharp transitions are gone, right? So this is what is done for filtering. This is why it is done, right? The filtering, right? We want to limit it to a certain bandwidth, right? And in case of unfiltered, the transitions are sharp, so then these components are significant and they are going to repeat because it really depends on how you sample it, right? If you have more samples, then you are going to have more of these, right? So you understand what I'm saying, right? So now next is, so for example, I'll show you. Let's make this 20 samples per symbol. And now you're having more of these repetitions, right? So you see, okay, so let's put it back. 10 samples per symbol. Okay, so blue one is what goes into the PA, and then we want to look at what comes out of the PA. So what goes into the PA is this one. This goes into the PA, and what comes out of the PA is V out. So this comes out of the PA. So you will see that, of course, there would be a repetition. You see, the spectrum is going to repeat because you are discretizing it. So, and when you discretize it, then the spectrum is going to repeat, right? Now, so the same thing is happening over here, but what is happening is that you have the spectral regrowth. So you can see that this portion on blue, okay, this portion is a spectral regrowth. On both sides you see the spectral regrowth, right? So this side, and this is because of the non-linearity of the PA, right? So on both sides you are seeing spectral regrowth, right? Okay, so now I am going to take the power up. So let's say if I increase the power from 0, okay, if I increase the power from 0 to, let's say, 10, okay, so now it will be putting out something like 27 or something, 28 or 29, or maybe it's 1 dB compressed, who knows. Okay, so now you see that this nonlinearity is more, and the spectral regrowth is more, and the ACPR has gone down, right? ACPR is basically this level, and this level, right? So in between what you have, this is your ACPR in dBc. Okay, so as you hit with more and more power, right? The spectrum, the or rather you can see the transition, right? So of course it got adjusted. It is going to basically go into compression, right? So when it goes into compression or nonlinear region, then the spectral regrowth you are going to see like this, right? And we have to determine what is this ACPR, right? So we will write some equations to find out ACPR, right? So now in this case your PA can be the transistorized circuit also. So right now I'm just using this one, but when you use a transistorized circuit you will see this thing is going to rotate also, while here you don't see any rotation because there is no phase relationship between input and output in case of this model, while in case of your transistor there will be phase relationship and this whole thing will rotate, right? Okay, so now let's go ahead and compute ACPR, right? So for that I'm going to write certain measurement equations. First of all, I'm going to decide a channel. Okay, so what would be the bandwidth? So basically this is going to be, total thing is going to be symbol rate. The whole bandwidth is symbol rate. Okay, so the main channel, okay, notice that when you do this uh, spectrum, it's around 0. Then 0 doesn't refer to zero frequency, it refers to carrier frequency, and these are the offsets, right? So you read it that way. So now here I am going to say that the main channel, okay, main channel is a aggregate. So the way you write aggregate is in curly braces, and it will go from minus symbol rate by 2, right, to plus symbol rate by 2. Correct? So it is going from minus symbol rate by 2 to plus symbol rate by 2. Okay, and next thing is, so this is going to be your main channel, right? And then you are going to have an offset, and then offset is going to be a band which is going to be symbol rate. So basically you will specify how much offset you want to, how much guard band you want to give, but I will give a band with the excess bandwidth of 35%, so 0.35 I will give to that. So I have to go to the other channel. The other channel, let's say, is going to be upper. That upper is going to be equal to main plus, so the entire spectrum is going to be shifted up by symbol rate, and I will provide an excess bandwidth which is 1.35 now, right? So because 0.35 is from the filter, right? So I will say add, and then the lower is going to be minus, okay, add. Okay, so this is done. So this I have specified in here, I have specified 3 different channels. One channel is going to be, let me just draw it. One channel is this. Okay, this, okay, so this is your main channel, right? And then I have taken the entire thing and shifted it by symbol rate divided by symbol rate into 1.35, so 35 excess bandwidth. So I have gone that way, and then I have also taken another which is over here. So I have got main channel, upper and lower. So I have got main, so this is your main, right? So and then I have got upper channel, so this is your upper channel, and then this is your lower channel. So let me just write down. So this is your lower channel. Okay, so you have a main channel, upper channel and lower channel. So this is what we have: the main channel, the upper channel and the lower channel, and I have a 35% excess bandwidth because of the filter, right? So that is for the scaling it out. Okay, so now what I will do is I will find out the power in this in this channels. So the way to find out power is, let's say main power, main power, main channel power is going to be 10 log 10 of 10 log 10 of something plus 30, because we want it in dBm. And what is inside? I will have CHANNEL underscore power underscore VR. So this basically is a inbuilt function to integrate the power in a certain bandwidth. And in that case, channel power VR, I have to specify here what voltage. So basically that is V out. V out fundamental, right? And then I'm looking this in a 50 ohm system. And then I want to measure it in an aggregate, which is main. Okay, so this is your bandwidth. Then I want to specify a certain windowing. So that windowing is KEISER, Kaiser window, right? So that is your main channel power. Okay, so you have channel power VR, V out 150, main Kaiser 30. So first of all, I'm going to check if this equation is correct. So I'm going to hit simulate. So there are no warnings. That means that that channel was correct. And let's look at what is the power level. So let's go to the table, and I'm putting in 10 in, right? So main channel power. Okay, so I'm putting out 10, 28 out. So it's almost, so let's back it off. Let's back it off to 0. Let's see uncompressed case. Okay, 0, let's put here 0. Okay, so let's look at the gain with 0. So the gain is 18.6. Have I done any mistake here? Have I done mistake here? No. Well, maybe the excess bandwidth should have been included here. But anyways, so I'm going to just treat this as my main channel power, right? So I'm putting in 0, I'm getting 18.6 out. Then I'm putting in 10, right? I'm putting in, not this one. Where is the other one? Okay, so I'm putting in here 10. So I have a gain of 18.6, right? So if I put here 10, then I have 28.6, but it is 0.6 dB compressed, right? So that's around 28.065, right? So now this is one power. So let's look at power which is above. So I would say, not here. Where is my equation? Here. So now I will say the same equation. I will just modify this. Main power upper, UPPER, upper power is equal to the same V out in a 50 ohm system, but instead of main I am going to have a spectrum which is upper, correct? And say add, and then the lower power. Okay, so lower power is going to be lower. Okay, so this would be lower. Am I right? Yeah, add. Okay, so we have that. Then the next thing is ACPR up and ACPR down. Okay, so next is ACPR up. ACPR up. So that ACPR up is going to be upper power minus main power. Main power. Am I right? No. Upper power minus main power. Correct? And so add, and ACPR down is going to be lower power minus main power. Oh, there is a mistake. That's okay. I will correct it. Lower power. So this is going to be upper power. Okay, so now we have got the ACPR numbers. Okay, so now I'm going to simulate this again. Okay, so now I will look at main channel power. Then I'm going to look at upper channel power. Upper channel power. This is in dBm. That is minus 15 dBm. Then the lower channel power. So this is the power spilt into the adjacent channel. So lower power. That's again minus 15. And then ACPR up and ACPR down. So this is minus 43. So this is your ACPR up and ACPR down. Correct? So now let's boost the power more. Okay, let's see what happens at the 1 dB, close to 1 dB compression. So here I am going to put here something like 12 and hit simulate. Okay, so now I'm almost 29.6, not 30 dBm out still. So I want to see what happens at 30 dBm out. So I'm going to put 12 and a half. Okay, and hit simulate. Okay, so I am putting out 30 dBm in the main channel, and my ACPRs are minus 37.5 and minus 37.6. So this is what your ACPR numbers are. Of course, they have gone up. So this would be, sorry, hang on a second. Okay, so the ACPR has gone up. Okay, so you can always plot ACPR versus input power, right? So this is where your non-linearity is. Okay, now all you see here is the amplitude information. You will also see the phase information. The phase linearity is important, right? So in the practical circuit you will see that also. Okay, so this basically, let me see how much time I have taken. Okay, 37 minutes. So I wanted to show you a QAM input, right? So I think I'm going to do that in the next one. In the next session, I'm going to show you a QAM input, QAM 16 input, right, into the PA, and then the output of QAM 16, and then I will do EVM on that. Okay, so I have shown you in this session ACPR, right, with a modulated signal DQPSK. You can put, so basically I'll show you how to do any QAM 64, QAM 256. Okay, and now Keysight sells you what is called virtual test bench, and if you don't know what you are doing, then you would have to buy that virtual test bench. But if you know what you are doing, you can do your EVM without virtual test bench, right? So let's I'm going to stop here. Thanks a lot. Thank you.